Welcome to this short course on probability and random variables. We shall introduce probability in this first lesson, and we introduce also some function that will be useful to calculate probability when the common sense alone is not enough. Let's see this definition of probability and pay attention to these words emphasized in red because they are important. The probability is a number that indicates the frequency with which events associated with a set of possible outcomes of an experiment occur. Let's read this sentence in the reverse order in order to fix the ideas. We have an experiment, for example, the random roll of a die. We have a set of possible outcomes of this experiment, and of course the outcomes are the number on the top of the face of the die. The set of all possible outcomes that is called the sample space includes all the integer numbers from 1 to 6, as well known, and an event is any subset of possible outcomes. For example, here we have the event A that includes number 1 and 2, and the event B that includes all the even numbers. Let's now move to a more operational definition of probability, and we introduce the relative frequency of an event A, that is simply the ratio between the number of occurrences of the event A divided by the number of trials. When this number, capital N, of trials become very large towards infinity, then the relative frequency becomes the probability. From this definition, this very operational definition of probability, we can derive three simple rules of the probability. Those are non-negativity. Of course, the probability of any event A is a non-negative number, and as a matter of fact, we have defined the probability as the limit of the frequency, and it is the ratio between two positive numbers, so it cannot be a negative number. Normalization. The sum of the probabilities of all the events is 1. And as a matter of fact, the probability of the sample space is 1 since numerator and denominator in the relative frequency are the same number. Additivity, this is a very important property, very useful to the computation of probabilities. For two events A and B, the probability that A or B occurs, that is the union in the set theory definition, well, the probability that A or B occurs is the sum of the probabilities of the individual events minus the probability that both A and B occurs together. That is the intersection, again, in the set theory notation. So in formulas we have the probability of the sum is the sum of the probability minus the intersection. Well, in order to understand the ratio of this formula, we can pass to the set theory notation. In the set theory notation, we represent an event A, for example, with this yellow rectangle here, and event B with the other rectangle in blue here, and we have that the union of the two events A and B are this area here that I'm following with the pointer. And of course, the area is the sum of the two areas of the rectangles minus the intersection, the green rectangle. So this explains quite well the formula we have written before. Conditional probability. This is really an important tool for the computation of probabilities. The conditional probability is the probability of an event A occurring given that another event B has already occurred. It is written in this form here, with this symbol here. Pay attention, here the slash is probability of A slash B. This slash is not divided. This is a particular notation in the field of probability and indicates the conditional probability. Conditional probability is strictly connected to the intersection probability by this formula here. The conditional probability of A given B equals the ratio between the intersection probability AB divided by the probability of B. And again, this formula can be quite well understood in the set notation. Again, we have our event A, that is the yellow rectangle here, our event B, this is a blue rectangle here, and of course, given the event B, the probability to have the event A is just the intersection, the green rectangle here. But in this case, all the sample space is not A and B, but is only B, and so we have to normalize by the probability of B. This is the rationale behind this formula here. Bayes' theorem. This is a direct consequence of the conditional probability. Since the intersection probability can be reverted, I mean the probability of AB equals the probability of BA, we can write this formula here. That is the probability of A given B times the probability of B equals the probability of B given A times the probability of A. And by taking these last two terms here in our equation, we can write the Bayes' theorem in this form. That is, the probability of A given B equals the probability of B given A times the ratio of probabilities. When we use the Bayes' theorem, well, of course, when the probability of B given A is already known, or in all cases where the probability of B given A can be calculated much easier than the probability of A given B. And now let's see an example that fixes the ideas on the importance of the Bayes' theorem. Let us suppose we have two sets of communication channels. We have 60% of the channels that are fast and 40%, of course, that are slow. So our sample space is divided in two populations, fast channels and slow channels. We know that 70% of the fast channels are wireless, we indicate that with W, and all the slow channels are wireless. And we want to compute the probability that we get a fast channel, F, after selecting a wireless one, W. In formulas, we have to compute this probability, a conditional probability. Probability of fast channel given a wireless channel. This probability is not as easy to compute as if we use the Bayes' theorem. And in fact, by reverting the probability, the conditional probability, we can write that the probability of F given W equals the probability of W given F, and this is given by our problem, because we know that 70% of the wireless channel are fast, and so here we have the probability 0.7. The probability of fast channel, again, is given by our problem here, 60%, 0.6. We have to compute the probability to get a wireless channel, and this can be computed easily by exploiting another theorem, that is the total probability theorem, that is a direct consequence, again, of the Bayes' theorem. Total probability tells that if we can have a partition of our sample space S into independent event B1, B2, Bn. If the sample space is the big rectangle here, and all the our smaller events are the colored rectangles over here. Well, if we have this condition here, every event can be computed as the sum of the intersection of the event A with the single subset of events B1, B2, B3. It's quite clear by looking at this picture here. So in formulas, the probability of the event A is given by the sum of the probability of the intersections. And again, by exploiting the Bayes theorem, we get that the probability of the intersection is the probability, conditional probability, times the probability of Pn, of course, under the sum of all the subset we have divided our sample space. Coming back to our example, here we have the probability to get a wireless channel, and we compute it by exploiting the total probability theorem by dividing our space into fast channel and slow channels. And all these numbers that appears in the formula of total probability are numbers that are given, are known from the problem. The probability to get a wireless channel given a fast channel is 0.7, the probability to get a fast channel 0.6, as seen before. The probability to get wireless channels, since the channels is low, is 1, because we know from the problem that all the slow channels are wireless, and the probability of slow channel is 0.4. We compute this number, we get the results 0.82. We substitute this number in our original equation, and we find our result. Results, I repeat, that cannot be computed quite easily without the exploitation of the Bayes theorem.